Hello and welcome to the final session of this winter quarters seminar series. Today it's my great pleasure to introduce Jonathan Balkind as our speaker. He is an assistant professor at UCSB, our UC colleague. His main interests are computer architecture, programming languages, and operating systems. That's very much on theme for what we discuss here. In particular, we've been focusing primarily on open source hardware, and of course, doesn't get much more open source hardware than OpenPiton, which he's worked on and lead architect. And not only is it open source hardware, it interfaces with other open source hardware projects, right? There's a lot of great interactions. There are a lot of great meshing and interfacing. And so please take it away. We're excited to hear about this.
Great, thank you. Yeah, thanks for that. I am especially excited to talk to another UC. I think Tim Sherwood and I were recently talking about how powerful the UC is with respect to open source hardware. So it's great to get this opportunity. And so I'm going to be talking about this cache coherent heterogeneous ISA system that we've been building. And the broad system is kind of some combination of something that we call OpenPiton, some combination of something we call BYOC, and something we call P-Mesh. And so P-Mesh is the memory system coherence part, and OpenPiton and BYOC are kind of frameworks that we've built around that. This is a pretty big project in general. So this started when I was in the first year of my PhD back in 2013, and we've been developing this platform since then. And so there have been a large number of people involved in this. I don't want you to get the idea that this is just my work. There, probably been 30 plus people involved at different points in time. At any given time, there's probably 10 or more people who are working on different pieces of this system. And so the part that I'm going to be talking about mainly today is the cache coherence system itself. This in the orange box here on the right is called P-Mesh, and it's a cache coherence system designed for building Manycore SoCs. And doing research in the kind of Manycore environment, we care a lot about extreme scalability, right? So we don't just want to be building little tiny things with small numbers of cores. We want to have the capacity that we could expand things very far, and be able to kind of have that forward compatibility. And one of the big things that we built into P-Mesh is called the transaction response interface. So you can see here, and there's a blue dotted line underneath the orange box. And that represents this interface that we came up with, which is meant to make it easy to connect different cores with different instruction sets and different microarchitectures into the system. And so you can see here kind of a sample of a few of the cores that you could potentially connect together. But overall, we've connected more than 10. I think we're somewhere around 13 or 14 at this point to varying degrees of functionality. And I think 5 or 6 different ISAs at this point. And so this is giving you, as a coherent system, that support to build heterogeneous ISA systems, right? So you can have these cores coexist despite the fact that they use different instruction sets. And then on top of that, we have kind of the ability to connect to different peripherals or accelerators using standard interfaces where those are available. And so this is really meant to be kind of ISA agnostic and open and available for connecting lots of different stuff into it. But why have am I bringing up heterogeneous ISA? Why might we be interested in heterogeneous ISA? Well, let's start by talking about where we're coming from, right? So, I mean, the original multi-cores and the original many-cores were single ISA, single microarchitecture machines, right? You basically just design a core and then you stamp out a bunch of the core and you connect them together with some kind of interconnect. But, about, I don't know when it was, 2003 or so, there was kind of a look at, well, what if we built a system where we had microarchitectural heterogeneity in a single chip, right? So we have some kind of multi-core, but we have, the cores in that system, they share an ISA, but they have different microarchitectures. And so this kind of morphed, and over the last 10 or so years, there's been this ARM Big Little, which has been a big push. And so just about any smartphone that you buy today will have a Big Little heterogeneous microarchitecture setup. Apple use it. Intel now even have a real product in the market that uses kind of the same heterogeneous microarchitectural capability. And the reason for this is that you can get a lot of performance and power benefits from it, potentially. So on the right hand side, you can see this chart from the early days of Big Little of the DVFS curves for your 2 cores. And so, you can push your core up into the higher frequency regime, and it will consume more power, but you'll get a lot more performance from it. And if you want to save power, you can move down into a lower frequency regime and you can save a certain amount of power. But you're still limited on this kind of single axis of frequency. And what heterogeneous microarchitecture gives you is you can add in another core or multiple other cores with different microarchitectural design points. And then you can choose to switch between the different cores to take advantage of their specific microarchitectural features. And in return, you can have a different amount of trade-off in terms of your performance or your power. And so the goal with heterogeneous ISA is to ask a similar question, right? Rather than simply saying, we're going to have a heterogeneous microarchitecture, you can say, well, what if I actually have a different instruction set? And are there inherent features to an instruction set that could give us benefits if we wanted to build a similar kind of multi-core environment, right? And so in the architecture realm, there's been some amount of research in this space. So there was prior work, a particular paper from ISCA 2014 by Ashish Balkind and Tulson, which showed that you can actually get performance energy efficiency benefits by building a system where you have cores with different instruction sets. And one of the key parts here is that they identified that applications and phases within applications have affinities to particular ISAs. That is, if you care about a particular metric, then you would want to spend some of your execution time running on a particular ISA and some of your execution time running on another. And so they show that there are different affinities according to metric you care about on top of that. So you can see here's a chart on the right-hand side that came from their paper, which shows for 3 different instruction sets, thumb, alpha, and x86 64, the portions of the execution time that you would be best to spend on each of those 3 ISAs for each of their applications, if you care about performance. And so, this varies depending on your application, right? BZIP2 actually has some time. You might want to spend kind of significant amount of time on thumb, whereas, for most of the other applications, thumb isn't necessarily a great choice for performance, right? And x86 64 is very heavily represented for MCF, right, as an example. But then if you care about energy efficiency, the chart actually looks a bit different, right? And so for energy efficiency, you see, for example, that thumb is more heavily represented. And in some cases, x86 is less heavily represented. And so this is kind of interesting finding, right? Is saying, hey, maybe you should actually think about this heterogeneity aspect you might not otherwise have thought about, even though it opens a big can of worms, right? Now, the thing that's missing from this work was that it was done in simulation because there wasn't any existing hardware that had a hardware coherent shared memory system to take advantage of. And so there was a kind of an assumption that there was a kind of Oracle memory system under the hood that you could take advantage of. But it wasn't, the simulations of each of the types of cores were done independently of each other. And so that's the kind of architecture side. On the operating system side, people have actually built heterogeneous ISA operating systems. And one particular example is Popcorn Linux. So this was set up in an environment where they basically have a big Xeon server, and then they plug in a PCIe card that has like some ARM CPU on it. And so they're using PCIe for kind of the synchronization between the different kind of kernels that they have in their system. And so it's relatively high overhead. If you want to synchronize things, you want to keep things coherent. So they don't really have a concept of coherence on memory. And then K2 is another example where they used an OMAP processor, and this had kind of ARM cores and it had thumb cores. And it was actually really cool. They were able to like build kernels that could like share data structures across the 2 ISAs because those ISAs came from the same company. But in neither of these 2 OS examples did they actually have an underlying system that had cache coherent shared memory, right? And so the question that we had was, can we actually build something where we do provide cache coherent shared memory to a heterogeneous ISA system? And could we do it in a way that would give us, reasonable performance and kind of, beat out these examples where you didn't have any underlying hardware supported coherence? And so the system that we built, we call Bring Your Own Core, or BYOC, because the intent is that people will actually bring their own cores and plug them in, right? And then we can start to do some really interesting research based on this. And some of the innovations that we had in building this, the first of these is that, yeah, we actually can connect a whole bunch of different cores in a single open source system, right? So previously, if you looked at other kinds of interconnect that were out there, they would often be restricted to only cores of a single ISA or even a single microarchitecture, whereas we were specifically trying to enable this to support different ISAs. And the P-Mesh component itself was essentially, we're taking this memory system from OpenPiton, enhancing it, and building something more extensive, is an open source cache coherent memory system explicitly designed to handle this heterogeneous ISA case. And so, you know, we haven't thought of everything, but we're pretty far along at this point in terms of the capabilities. The other big innovation here is the interface that we provide, which is called the transaction response interface, which is named after our group mate Tree. I think Mike's in the audience, so Mike will have a laugh at that we called it that in the end. And in building this stuff, we built, you know, a variety of different cool prototypes. And one of those was what we think is the first open source general purpose heterogeneous ISA processor. It's called JuxtaPiton. And so this makes use of our BYOC memory system. So where do we start in building this, right? We want to actually have, you know, variety of capabilities here. If we want people to be able to come along and build new heterogeneous ISA systems that they never thought of before, or if they want to come along and kind of like build an OS on top of something like this, you know, we need to provide prototyping capabilities, you know, ability to take this thing out. You want to be able to put it on FPGA and run real software on it, right? So we started from the OpenPiton system that we built, virtually the same team at Princeton. And so OpenPiton itself is an open source Manycore research platform. It is actually a Manycore processor design, and we open sourced this back in 2015, but the implementation effort started back in late 2013. So this has been going on for quite a long time. The design itself is written in standard Verilog RTL with some Python for, you know, assisting in pre-processing and so on. So you don't need to go and kind of like learn some new weird hardware description language to make use of it, or you know, if you've only been taught in an old school class that only taught you Verilog, then you'd be able to kind of get to grips with OpenPiton. And one of the big things is, right, this was designed to be an open source research platform where people can, you know, change the sizes of things, particularly architects, right? So they want to like change a bunch of different configuration parameters and test out their research widget according to, you know, the design space that's available to them. And so we provide a lot of configurability there, but then we also provide a validation suite. So you can test if, you know, you go in and you modify the Coherent system in some way to add some capability that you didn't actually break the rest of the Coherent system in the process. We provide simulation with pretty much every major Verilog simulator that's out there. And this is actually really useful, right? Because now you know that the code base will work regardless of which simulator you use, maybe except for some of them are not so full-featured, I would say. And one of the really cool things is that actually the developers of Riviera Pro Aldec, they actually added support for OpenPiton themselves, and they PR'd that to OpenPiton because they wanted to check that, you know, their simulator would get kind of the same behavior as other simulators we're seeing. OpenPiton provides a synthesis and backend flow, which is somewhat unique. So if you have access to the synopsis reference methodology, then you can basically get our synthesis and backend flow and be able to tape out your own chip based off this stuff. We have actually taped out real chips, multiple real chips based on this platform. And there's even a characterization I'll talk about a bit more. And the chips or FPGA prototypes themselves can actually run real Debian Linux. And so you can take existing software and then, you know, test the scalability, or, you know, you can make minor modifications to software to support new hardware features that you add, and then test them in a real OS capable environment. So, you know, one example that we have is if you want to do FPGA prototyping, right? We support a variety of different boards that you might want to use. They kind of run the gamut in terms of price and number of cores supported. And, you know, different people come along and they say, I want to support some other board. They add support themselves, and you can kind of find some of the forks online where people have added those, maybe call it like a tier 2 level of support or something like that, whereas it's not boards that we have ourselves so that we can validate so well, but it's generally pretty easy, right? We support a bunch of different boards and people are adding their own as well. And then on the chip side, we built this chip back in 2015. It's called Piton. So this was a 25-core chip that had 64-bit SPARCv9 cores. And this was taped out in IBM's 32-nanometer process back then. It's a 6x6mm chip. Unfortunately, I don't have one to wave at you, but you can see the pictures in the slide. And it has just under 500 million transistors. So at the time that this taped out, I think we ran on the same run as the people who pipped us in terms of absolute size and number of transistors. Since then, there have been several bigger chips, of course. But this was, you know, one of the biggest chips built in academia, even today. And we have the real chips, right? So these, we have this like gun box that we would take to conferences where we plug the chip into the board and we'd be able to show the real prototypes running. And so you can actually see the picture here of the test setup where you can put the Piton chip in, you can have it connected to a desktop power supply, and you can like boot Debian on this, right? You can run various different applications on the real chip, and we can also characterize it. And so that's what a bunch of the logic is for. And so one of the things I want to note additionally here is like, this chip was like a place for us to test our research ideas, right? So we had, I think, 3 different research ideas that went in, and I suppose as one of our collaborators had an idea that all went into this Piton chip. And so, then we were able to take that in different ways and characterize it and verify what we did, right? And so in doing so, we, have both an open source design, and then we also open source data, right? And so you can kind of correlate characterization results back to the original RTL, the design decisions that were made at the time. And then from that build, new useful research ideas, and, figure out, oh, did my thing actually work? And so we released like just about everything we could possibly release online. So there's data, there's hardware infrastructure, assembly tests, micro benchmarks, the board designs are all open source. And so Mike, who's in the audience, would be able to tell you many, many, many details about how this part of the system works. But what's crucial here is it's open and available, and you can make use of it to enable your own research. So this is where we were starting from in building BYOC and extending P-Mesh. So, we started out and we had kind of an OpenPiton tile that we could take here. You can see on the right. And, in the beginning, when we were starting, right, this only supported the OpenSPARC core, right? And so this was a great core when we started out, right? And we were writing RTL from like 2013. And so there weren't a whole ton of options available at the time, and we wanted OS capability, and we wanted hardware multi-threading. So this is what we settled on. And it was great because we could actually boot a real, OS distribution and enable a whole bunch of research. But if you think about it from this generalization perspective, we're trying to zoom out and support a bunch of different cores and so on. Like, there was a bunch of places in the design that were kind of very specific to SPARC or specific to this particular microarchitecture, right? And we had this like CCX bus that came from the core itself, and that's how the FPU connected and so on. And so we wanted to kind of step back and say, how can we connect other cores into this? How do we support other ISAs? And so what could we connect? Is one of the questions. And today, in 2021, we have a huge number of different open source cores that we can work with, right? And so you've got a variety of different instruction sets that are represented today. And there's been this kind of big emergence of open source hardware, right? And so OpenPiton has been kind of part of pushing that along. And I think one of the things that's really exciting here is then we have the ability to start connecting to all these really cool open source cores and other research and developments being done in the open. And so, yeah, I guess when we started out, like, there was probably like maybe 7 of these cores were available or something like that, or maybe fewer when we started in 2013. And now there's just so many. And so if you want to come along and like connect new cores, right, like you need a way to interface the cores into the system. So we had several options on how we did this interfacing, and those have different trade-offs, right, with respect to our goals. But one of the key goals that we wanted to have is minimizing the effort needed to connect a new core, right? We want to be able to connect them in, have them be coherent, and work together in a heterogeneous ISA environment without having to require a lot of changes. And we want other people to do it because they get the benefits. And then we get the research capability out of them doing the work. So the first option that we had is we provide 3 levels of cache to the end user, right? And so we provide last level cache, a layer private cache, and then provide an L1, right? And anyone who's done a significant amount of architecture knows this kind of non-starter, right? You're not really going to provide somebody with an L1 because it's so tightly coupled to the course microarchitecture, to ISA details, and it's a kind of a high bandwidth, high performance, low latency design point that you need to connect there, that black dotted line. So this was kind of out the window immediately. But another possible option, right, is that we provide just the last level cache from our system. And then the end user can connect their core with their L1. They can modify their L1, or they could, add a layer of private cache. But basically, they would have to implement the rest of the coherence protocol in order to connect into the system. And the trouble is, coherence protocols are notoriously hard to validate. It's not an easy task, right? The P-Mesh system has 36 different message types or something like that in it, right? So there's a lot that needs to be validated. And so it's very likely that people would come along and build implementations that were very subtly incompatible with each other. And then you would be kind of stuck. You wouldn't actually be able to build this heterogeneous ISA system you want to build. So we settled on a third option where we provide the last level of cache and we provide a layer of private cache, and those encapsulate most of the coherence system details. And so that means that we can, hopefully keep the validation that we need while providing the end user with the ability to reuse their core with its L1, and they just have to implement this dotted line, the interface. So the interface itself is called the transaction response interface, or tree, and it's designed to be simple in terms of the number of message types that there are, extensible in that you can choose which subsets you want to implement based on the functionality that you want to have in the system. And it's intended to be low overhead, right? So in terms of state machines and other kind of logic that you might need to connect to this interface and have your core become part of the system. So far, we have implemented connections of a bunch of different cores ourselves and with collaborators. And even some external people have come along and connected. And so the main cores with the most functionality in the system. So obviously we have the OpenSPARC T1 that came with OpenPiton. And so as we developed this transaction response interface, it also developed along with that. And so the functionality was maintained. But we also support Ariane and Black Parrot. We've implemented all of the subsets for those. And so they can boot SMP Linux in our FPGA environments. And I guess in simulation, although it's very slow, I don't know that you'd want to do that. We have the Pico RV32 core. So this was the first non-SPARC T1 core that we connected into the system. We had 2 Google Summer of Code projects via the Free and Open Source Silicon Foundation, where students were working on connecting the AO486. This is an open source re-implementation of Intel's 486SX CPU. So that's pretty cool. We can actually run the BIOS and stuff. I'll tell you about that. We've connected QEMU, so that gives us capability of a bunch of different ISAs that we could potentially use. And then the last one I'll note here is Manycore. So Manycore is an OpenPOWER CPU. And I spent a few days, I actually don't know VHDL, but I tried to pick it up for the purposes of connecting this core. And I was able to get to the point of implementing the instruction subset to significant degree completeness, and then some amount of the load store subset. So I could like, print like HE out of Hello World or something like that to you. But that's the amount of functionality that you could potentially get in a core that kind of corresponded well with our design. So the first proof of concept that we built was using that Pico RV32 core that I mentioned. And so we believe this is the first open source general purpose heterogeneous ISA processor. And it has a 64-bit SPARC T1 core, which boots Linux. And then we have a kind of this embedded 32-bit RISC-V core Pico RV32, and the two of them can actually coherently share memory. And so the SPARC core actually runs Debian, and then we can you run in some stuff in the terminal, and you can / a 32-bit RISC-V binary, and rather than telling you, I don't know what that is, it will actually transparently offload it and run it on the Pico RV32 core. And then it can proxy any syscalls back to the SPARC core in Linux that it needs to for operation. And so this was kind of the first taste that we got, right? That this was a potential thing that we could do. And so our BYOC and our JuxtaPiton papers kind of have some details and understanding, doing a very surface level comparison of these two cores and how they work in the system that could, then build into something bigger from an architectural perspective. This design is also open source and upstream in OpenPiton, so you can actually go and reproduce this. You can download the code and build this or other similar systems. And so this kind of gave us a taste that we wanted something more complex, right? And so we wanted to be able to connect an actual other Linux capable core and be able to test something more interesting, right? And start to investigate OS implications. And so I started up a collaboration between ourselves at Princeton and the Pulp team at ETH Zurich to connect their Ariane core into the system, right? So our goal was to develop a permissively licensed Linux-capable Manycore research platform based on RISC-V. You can think of this as the RISC-V version of OpenPiton, right? And so we were coming together with two pretty mature and extensible designs. Ariane was able to already boot Linux and had been taped out, and OpenPiton had been taped out and could run Linux with the SPARC core. So within less than 6 months of a couple of us kind of working on it on and off, we were able to get SMP Linux booting in the system, right? And so as people do system bring up, this is pretty quick. But additionally, what was interesting about this is we booted Linux single core for the first time on a Monday. And then on the Tuesday, we booted dual core. And the following Monday, we booted quad core. We didn't actually change any RTL in the interim other than the instantiation for the number of cores. And so this actually showed really kind of the power of trees and interface. We could actually bring in a new core of realistic complexity, one that can actually boot an OS, and then benefit from the validation that we've done to the memory system already in terms of this kind of ISA-agnostic functionality. But of course, there were changes we had to make in the system to actually make this possible. So I'll talk about those. So an OpenPiton+Ariane tile looks a bit like this. You've got the kind of Ariane part on the left and the P-Mesh part on the right. This is basically the same picture I showed you earlier, but turned around. What were the changes that we had to make? Well, in Ariane, we made, or the Pulp team, I should say, made changes to make a new write-through cache subsystem, which supported invalidations, because before they were only single core. You need this capability to validate the L1s, and use our transaction response interface. On our side, in the P-Mesh side, we needed the new atomic operations for RISC-V that didn't exist in SPARC. And so we added low reserve stroke conditional into the L1.5 cache, which is a kind of good place to put it, because then you can reuse it in other cores as well. And then we also added fetch and op atomics into our L2. So we could kind of reuse some of the way that we did swap and compare and swap in SPARC, add in a new atomic ALU, make some other modifications to make that work. And then the other thing that we needed to add was platform support. And so, we needed to have a boot ROM for the system. We actually auto-generate the boot ROM and the device tree for the boot ROM based on the specific configuration that you're building, right? So we have support for a huge number of configurations, right? But this will actually build you the correct one into your device tree and your boot ROM. We support kind of the standard RISC-V debug, clint and plick for platform peripherals, and you can actually use a debug unit on FPGA and use GDB to single step execution of real stuff. And what's cool about this, additionally, that I really want to highlight about open source and open standards here is that we can reuse these platform devices for other cores, right? So we've been working with the Black Parrot team from the University of Washington to connect Black Parrot into the system, and we can just reuse the clint and the plick and the boot ROM from this setup with Black Parrot. We haven't tested debug, I don't know what that is, but for the others, we can just directly reuse them from the Ariane setup. And so this is really great. If you come along, you want to plug in a new core, it has a different microarchitecture or something, you can actually reuse all the stuff that's already available. So this is great. So having built this, right, then we can say, okay, can I build some interesting heterogeneous ISA system, right? And if you think about it a priori, if your goal had just been let's build a RISC-V version of OpenPiton, then the answer might be no, right? No, I figured out how to switch everything over onto RISC-V and that's it, right? But we actually really cared to make this heterogeneous ISA system. And so the prototype that we built is called DICO, and this has 64-bit OpenSPARC T1 core and a 64-bit Ariane core that live together in this one system. And they both have fully hardware coherent shared memory, including the ISA-specific atomics for SPARC and for RISC-V. So each core can boot an independent Linux kernel, one for each ISA, and then we can run user mode applications on top that share memory across the two cores, across the two ISAs under the hood, right? And so this now then gives you this interesting capability, and you can start to say, what sort of OS level or software level problems could I try to solve with a system like this? And in the spirit of open source and making things available, we had an artifact evaluation done as part of the ASPOS submission. We opted into that. And so you can actually go and download all this stuff and reproduce it. And the prototype code is also available on GitHub and the BYOC repo as well. And the paper actually has an evaluation of round trip latency and throughput between these two cores, using shared memory, using the ISA-specific atomics for synchronization, using regular loads and stores for synchronization. And so I'm going to show you a quick demo of that in action. And so what you're going to see here is we're running a real FPGA, and we have two serial ports coming out, one for SPARC, one for Ariane. And we're going to boot Linux on both of them at the same time. And this will skip through to get to the interesting part, right? But on the left-hand side, what's going to happen is the SPARC core we're going to run an application there, which is going to map a physically contiguous memory region and then store the address of that region into some shared location. And then on the right-hand side, what's going to happen is that Ariane is going to run another program, which is complementary, which reads from that shared location, and then it's going to mmap its own virtual memory mapping of that contiguous region. Then the two cores are going to synchronize and pass tokens through a queue that's in that shared region. And they don't really know that the thing on the other side is running a different ISA, is using different atomic operations for, to deal with the queue. but they're actually capable of communicating with each other this way. And so, we measure out what the round trip latency is here for this, and it's in kind of the 70, 80 cycle range, which is pretty standard in terms of the types of synchronization that we're doing there. But this is way, way faster than the things that you would have built in the past where you didn't have this coherent shared memory under the hood. Other quick notes before I finish up here. So I mentioned about this x86 thing, right? So we had 2 Google Summer of Code students who wanted to connect this AO486 core. So AO486 is a really cool core, right? So somebody actually sat down and implemented an AO486 SX compatible Verilog RTL code base, right? And they built the whole SoC. So with this thing, you can actually like boot Windows 98, or you can boot like real Linux kernels on it. And it's actually being pulled into the Mister project, which is a platform for making a video game emulation using FPGAs. And so you can actually like, emulate some old DOS games and stuff like that on it. So this is a really cool setup. And what our students did was build ways of transducing from the AO486 core's memory interface into BYOC using tree, right? So the first thing we'd done was using the Avalon interface that provided natively, that it provided, and then we moved on to using the native interface that, basically it was already transducing from a native interface to Avalon. And so in the BYOC environment, we can actually run the real x86 BIOS with, some code commented out that we don't actually use. And we can run a simple OS on top of that, simple kind of boot sector programs on top of that as well. And we keep around the existing legacy peripherals like the clocks and interval timers and interrupt controller. And then another thing that we've done, I mentioned this in passing, was connecting QEMU into BYOC. So there's a group at Xilinx who've been building a system that's called libsystemc TLM SoC. And essentially what it is a way for you to connect QEMU emulation to RTL simulation. And so they use this for prototyping kind of different RTL designs where you might otherwise put it on like a Zinc or something like this, right? So instead you can do this in software simulation, and that gives you better visibility into your design. And so we were really interested in this, right? Because if we could make use of this, we could connect QEMU into BYOC, and then you could have ISAs that we otherwise don't have open source implementations of, right? So you can imagine x86-64 or ARM or other things that are out there. Even some weird legacy ISA that just never seen before. And so the level of functionality that we got to with this was kind of a few days. We were on a DARPA program together, and we kind of had a hackathon for a few days. And so we actually built versionless where they could do loads and stores into a cache that they had that was in system C. And then we just implemented a transducer to talk tree into BYOC. And so you could actually boot Linux in QEMU and then do loads and stores into a region that was mapped into BYOC. And so this could actually be pretty useful then for you to try and build other interesting prototypes on top of. Okay, and then, so this is my last slide here. So, the big thing that we're having here is that using OpenPiton or BYOC gives you all of this nice heterogeneous ISA P-Mesh capability to, whatever core you add, regardless of ISA. Now, obviously, there's asterisks to this, right? There's caveats there and not every ISA or not every microarchitecture is going to be a complete 100% match for this, but the general case. We had some students who actually, for a class project, they implemented a supposedly ISA-agnostic hardware transactional memory system in P-Mesh, right? So they could initiate transactions into the private cache here, and then try to commit, and it would correctly kind of commit or abort or whatever. And that actually didn't use any ISA-specific features of the core that was being used. And so that was a pretty cool setup. Ongoing improvements that we're trying to make, or ways that we want to enhance the system. So we have chip tapeouts in progress. And when I say in progress, I mean very in progress, like deadline is within days. For one chip, that's a very large scale chip that makes use of some of the capabilities of P-Mesh, not necessarily well, I suppose it does have some heterogeneous ISA capabilities. This is a very large chip, probably on the order of billions of transistors. And then we also had a tape out in the fall and kind of October, November timeframe of a smaller chip that was more kind of on the scale of Piton. And so I'm sure you'll hear more about those in the future, but we're really excited about those, and this gets us to kind of demonstrate some of this newer capability we've been building. Some other things are kind of, want to see enhanced support for the microwatt core, right? Is OpenPOWER. It's really interesting because Power has very good kind of Linux distro support, software support in general. And, it's also an open ISA now. So we're very interested in that. It would be cool to support more cores in ISAs, not just using QEMU, but in general. We're working on kind of different bridges that support other standards. It'd be great, for example, if we could connect to other open source coherence protocols. That'd be awesome. And then working on other interesting things, could you connect like clusters of cores per tile into this kind of system? Okay, so I'm going to stop talking here, and I'm happy to answer any questions you may have.
First of all, thank you for a great talk. And everyone else is probably remotely clapping as well. Yes, please ask ahead.
So while the students are posting some questions, so it's nice work, a lot of work there. If you are mixing different ISAs, you are also mixing different consistency models.
Yep.
And you have that on the cache, on the coherence. So I think that many of the issues might not matter because you have on the core, but you start to share the kernel, things like that, or you start to share anything. So how do you handle that?
Yep, this is always the first question that comes up when I present on this. So we provide basically guarantee of TSO on what we call a memory thread. So basically kind of one port into the private cache that we provide. And so if you want something stronger than TSO, you can you can bury your core, fence your core in the right way to not send requests into the system in such a way that TSO is too weak for you. And then if you want something weaker, if you want to get more performance, you can actually make use of multiple memory threads. So this is what they did with Ariane. And then you can keep track of the metadata in your core to make sure that you respect your consistency model in the right way. And so we talk about this a little bit more in the paper, but that's the high level gist. And so far, we haven't seen any consistency bugs. We have run Litmus, DIY Herd, Shadowclaps tool suite on it, and we haven't seen any consistency bugs that I remember. Or the things that we originally saw were functionality issues, not consistency bugs in the first place when we first ran it.
Dovetailing on that same question, yeah, I have similar questions. This is a really impressive accomplishment to have this heterogeneous, ISA situation where, I think you kind of touched this briefly in your talk, how, you have your cores interface, not just through memory, but also through this tree interface, which includes things like support for interrupts and atomics. I think I saw on a slide elsewhere, you had things like, your PLIC and your boot ROMs elsewhere on the mesh. Even still, there's just a lot of complexity for given ISA of whatever there is for between cores, talking to the platform. Is there any other like ports you need to talk to things, or any other complexities or headaches that came out of this kind of stuff? Or
I'd actually say I think we were a bit surprised that was kind of enough.
Oh wow, that's great.
For the most part. Of course, we haven't done something yet where we try to hook together interrupts handling for multiple different ISAs at once, right? And that will have its own set of complexities. We'll be kind of talking about what to do there. I will say one of the interesting things there is that a certain amount of this platform stuff is actually it doesn't need to be completely tied to an ISA, right? Like you could come up with a way to do it that would be lower performance, but you could potentially use the same device for multiple cores with different ISAs. And so for some of that stuff, I'm actually kind of interested in the direction that could go in, right? Of like, if you can now provide the right platform peripherals there, could you build an alternate platform, right? And for some ISAs, alternate platforms are just things that happen, right? Like, you build with ARM, you build with RISC-V. People just build their own platform peripherals all the time. Whereas for others, there's doctrine, and that's, like x86 has one standardized platform, and you would use that standardized platform. So I'm kind of interested in some of the space there that we could find. I think that, once you get in and you start to really think about platform details for more ISAs at once, there will probably be other kind of things that you'll discover that you need to deal with. But the level of the complexity that we kind of got to here, it wasn't a bunch of stuff that we'd see.
Great. So one case I was thinking in particular that might have come up already or not, perhaps, is things like IRQs between cores for like sleeping threads and multi-threaded scheduling. Does that come up for you guys in your
no, because
project so far?
No, so the environment that we were using, that DICO environment, only has a single core on each side, right? And so,
great. Okay.
Right, so that makes things easier. We could instantiate more cores on either side, and those are independent domains from each other with respect to all IRQ related stuff, right?
Sure.
So if you want to signal to the other core, you would have to do that via shared memory with the way that we have that set up today. We have a mechanism that internally that we've been building to enable us to allow like an IPI that could go across ISA, but we haven't built all the software support on top that you would actually want to then, make use of.
But cool, this is very neat stuff. I think I'm gonna keep quiet for a second. If you have a question from one of the audience members, maybe I'll go ahead and read it out loud. So it sounds like it might be beneficial to be able to swap out those cores without having to manufacture a chip again. Have you investigated embedded FPGAs for this? Then maybe you could avoid QEMU. So what do you think to that?
Yes, you can do that. I don't want to give away too much, right? But this is something that we've been actively working on. It's definitely doable. And I think, it would be really cool to be able to put a core or something else on that fabric, right? And, there's a question there of like, how do you provide an interface that then into your cache coherence system, but then, the FPGA can't just do whatever it wants and then, break the rest of your system, right? And so there's questions that have to be answered in that space. So there's one piece of work related to that called Crossing Guard that was ASPLOS, I'm gonna say like 2016, 2017, somewhere around there, which was on, could you have an interface for accelerators and have that be somewhat arbitrary and provide the features the accelerator wants with respect to a coherence system without breaking the rest of the coherence system when your accelerator misbehaves, right? And so there's similar questions to be answered in the space of connecting an FPGA into your coherence system. And so, yeah, that's an interesting thing to try and tackle, say that much.
Great. I think I'll pause for a moment if there's any more questions from the audience or other panelists.
So, because one of the things we look in is tools and infrastructure. So those are big systems that they have a lot of cores and a lot of things. What are the main pain points from a tool point of view? What are the things that you find that it's a problem that would like to change?
One of the big things that we've been hitting with our most recent tape out, I said this was kind of like billion transistor scale, is like, we need to be able to do gate sim of a certain amount of functionality, and it is excruciatingly slow for obvious reasons. But there might be things that we could actually do about that in practice, right? I'd say that's one of the big things. We had to come up with different layers of the hierarchy for backend to match, so that we could actually, you can imagine here, right? Some of the things are common across all of your tiles, and then you have different cores or other things that are connecting in. And so we had to come up with certain hierarchy for how we did our blocks for the recent tape outs. And it'd be really great if it weren't so much work to add a new block, right? I don't just mean like in terms of scripting and stuff. I just mean like fundamentally, like I add a new block into the system, and now I need to, have that whole multiplicative effort or something, right? It's like, so it's linear effort with the number of types of blocks that we support, right? So you're like, oh, we're gonna add a new core. This is great, right? This thing's open source, I'll just reuse it, right? But then actually the backend effort is commensurate. And so if there were good ways to, take advantage of existing, floor planning and things like that, that would probably save a lot of effort, I would say. Yeah.
Okay, and in simulation, so I guess that you are using quite a bit of FPGA for simulation because non-simulation is not fast enough. But then how do you deal with the observability issues that usual FPGAs have?
So I will say for some chunk of the stuff, we just get lucky that our stuff was well enough validated previously in the smaller scale that we haven't seen that many serious issues at greater scale. We currently have somebody who has an issue at larger scale, and we actually don't have a board where we can reproduce it. And to do this RTL simulation is like completely infeasible. And so we're like trying to work out a way at the moment to like be able to reproduce this this particular case. Yeah, so if there's anything that could help us in that avenue, it would be like really, really useful for us. Yeah.
Okay, thanks.
I think we have a question from a known audience member, so let them speak. So we're gonna go ahead and let them talk.
Hello, can you hear me?
Yes.
So I have a question. One thing is, can you please reshare that slide which showed the performance figures?
Performance figures
that were observed for BZIP2 and SGENG, all those.
Oh yeah, so this isn't my own work. I can show you that, but this is from the prior work. Yeah, here.
Yeah, that is fine. Like my question is, beyond the implementation, are there any? Can you please explain this? Do we have any insight into the performance benefits that are achieved with this, and based on that we can maybe draw a future pathway kind of a thing, that where it is kind of fitting very well, so it's definitely going to come up in the future in this domain of computing kind of a thing?
So, yeah, so this this part of this work wasn't trying to show that there was like what this part of this work was not trying to show what the magnitude of the benefit was. It was purely trying to show like that there existed an affinity and that there was a performance advantage or an energy efficiency advantage to running, you know, different parts of your application on different ISAs. If you look further into this ISCA 2014 paper, which is an excellent paper, I highly recommend it. I presented it to my students in class today in my advanced architecture class, and they specifically do call out, like, you know, these ISAs have these certain features and we see benefits for particular applications with respect to those features of those ISAs. And, you know, this is the magnitude of the gain that you might get if you built kind of some sort of heterogeneous ISA system. And so I would say for those particular details, I would suggest that you take a look at this paper, because it's excellent and it does set out the roadmap. And in some ways, we're kind of filling in part of what that roadmap would be, I would say. And there's been a bunch of other work in this space since this paper as well, where they look at like scheduling mechanisms. There was a paper that preceded this one, which looked at how to transition applications across different ISAs as well. There's been some other stuff in the space.
Sure, I'll look into that paper. And any other non-implementation related, at least maybe some other work that gave the initial requirement, not the idea that we can make the ISS, we can bring various ISS together, but at least an idea that we are getting into a computing mode where sort of such a thing could be required. Not how to bring it, but such a thing could be required. Is there?
Yeah, so that is the gain of this particular paper, is, you know, to show that like there is advantage to it. And so you should consider it if you care absolutely about energy efficiency or performance, right? There was the prior paper was by Device. I think it was also, Dean Tilson was also the advisor in that paper, which was slightly earlier. It's cited by this one. And it was looking at the transition mechanism and trying to make some arguments related to that. There were then, I want to say, 3 more papers from that group, I think, that were in this space. There were also, you know, pure architecture papers showing like there is an advantage to this. You know, you should try and seek this out. And then there were groups like, I think it was a paper from someone at EPFL, I can't quite remember where it was, where they looked more into the scheduling side and showed, you know, scheduling wise, if you schedule the right way, that there's a performance benefit to do it as well.
And one last question. By any chance, from your work or from any of the work that you are referring to here, did they actually compare the final results against the results of different kind of big little of ARM or a similar thing with RV32 where there is no ISA incompatibility to overcome?
Yeah, so there was actually in this exact paper, the ISCA 2014 one, there was a kind of baseline comparison with a big little of I don't remember what the ISA combination that or so the specific ISA that they were using, but they did do some sort of big little comparison.
And they found performance benefit.
Yeah, there was a benefit over that. Yeah.
Wow, that makes it very, very, very good actually.
Yeah. But I mean, you also open a huge can of worms when you do this. So it's like suddenly you have to worry about like ISA incompatibility in all these places that you never need to think about it before. So the big question I think is like, is the cost low enough for it to be worthwhile to do this, right? Or like, can we build the infrastructure to make it possible, right? And so that's the part that we're trying to tackle.
Just a general question. By any chance, are you aware if some industry has taken this up? This is a very general question, if I understand, but there's a very good chance if somebody would start it at some level, you might be involved in it. So if some company, some industry has, some big firm has already taken some steps in this direction, then especially with 32 and ARM coming up, many might be interested.
Yeah, so I'd say it looks costly enough to a lot of people that I think it doesn't immediately look interesting to them. The pitch of being able to reuse existing cores, I think, could assuage some of that concern. People, like in the case of Popcorn Linux and K2 on the next slide, like they were using existing systems for this, right? And so my understanding was there was a certain amount of interest in both those platforms. But I don't know of any specific examples that I could point to where somebody was like, yeah, we actually implemented something that looked the same, and particularly not that had coherent shared memory, because we don't know of anyone doing that.
I think the memory is a key distinguishing feature. I mean, I think it's well established that, many SoCs have shipped with multiple ISAs on them already, right? It's just that those particular cores may be deeply buried in some IP block, and it's not necessarily talking via coherent memory, right? And so I think coherent memory is an interesting twist. I don't think it's perhaps as scary if somebody were to perhaps do it in RISC-V world, where they had RISC-V cores perhaps more in a big little configuration, and perhaps those cores may have different extensions to them. And so in that case, you can argue, is that multi-implementation, or is it the same ISA or different ISA? I don't know, depending on which extensions are present. But I think that's maybe perhaps the near-term solution, or maybe that's just me espousing the party line. I don't know.
So I mean, like if you look at Popcorn Linux, right? I mean, the original Popcorn Linux was a Xeon machine with a Xeon Phi plugged into it, and the Xeon Phi was like, whatever it is, 32-bit x86 plus a whole bunch of vector and other stuff, right? And then the host machine was x86, 64, and so that was referred to as heterogeneous ISA. It was, there were clear differences there. They had a subset that was compatible between the two, but there was still a significant difference. And so I think if they can call it heterogeneous ISA, then we can probably call, significant differences between, different RISC-Vs heterogeneous ISA too. Yeah. And particularly since 64 and 32 are not binary compatible as well.
Great. More questions from the crowd. Once again, we can either narrate the questions for you, or you can request permission to speak and we can permit it. Or we can congratulate our speaker on a talk well done. Once again, thanks for coming and a great talk.
Thank you for having me.
Good job.
And looking forward to the next time we can all interact in person.
Yeah, exactly. Hopefully not too long. I hope you all have a good day.
You too. Have a good day.